had taken a beam. I think I have already given what is a beam, and then it was subjected to a central point load P, and then after going through the conditions of equilibrium, we could find out the reactions here will be P by 2 and P by 2. Though this point is this is a hinge, the reaction is only vertical. There is no horizontal reaction because that will cease to exist because there is no horizontal load. But otherwise it is a hinge. Hinge is required to keep the body in place. If it is not hinge, because you will say, no sir, these are only vertical reactions are there, so just rollers will do. Then you will be in a stable position, the body will not be in a stable position and it could be rolled on the floor. Its position will not be uniquely defined in space. Is it clear or not? So, the body's position will not be uniquely defined in the space. You have to fix the body somewhere in space. So, in x-ray plane, if anything is not clear, please stop me and ask. But don't keep quiet. So it is like this. So this is the free body diagram. Now, what is the status at any cross section at a distance x from the left hand? See, we have given already the concept of stress by taking sections, by putting a plane, by cutting the body into two halves, and then saying that there will be forces of interaction that will exist there, and then we have taken a point and we have shown around the point there will be some distributed forces. That forces we have taken normal force and then the shear force, and then we said that we define intensity of force as a stress, and there will be, so at a point there will be stress, normal stress, shear stress and so on. Now here we are talking what is the nature of forces at a distance x from the left end if you cut this body into two halves. So there is a reaction here, P by 2. In order to keep this in equilibrium, because this left part and this is the right part, I will slightly displace it so that I can show it. So here is the reaction, P by 2, this is the center point, P, and this distance is L minus x. We want to now understand what is the nature of forces on the cut section. Now please, I think we have already made our position very clear that we are considering a beam which is a planar, which is lying in xz plane. The width of the beam is very, very small. Width. We have applied the load in the plane, a vertical plane of symmetry, so that there is no twist of the beam. Horizontal line of the beam in the cross section will remain horizontal. So all the points will displace by the same amount. So here at any cross section, of course, I have already given you in a general force system, you have got at any cross section, when you cut it, you have got 6 forces, 3 normal forces and 3 moments. Now here, because it is a planar, so you will have, what do you have? In order to keep this in equilibrium, first of all, this is P by 2, so there must be a vertical force in order to balance this here. There must be, now I will draw this positive on the left face, that means on a face which is positive x. This face is a positive x face, this face, because outward normal is in a positive x direction. On a positive face, I will draw things like this. I will show, yes, on this face there will be a vertical force like this. You will say, no, why it should not be there? I am taking a general case. Vertical going in the Z direction, positive in the Z direction. Actually, it will be downwards, but then I am taking in the upward direction. Then, now this one, if it is there, so this will cause a rotation of the entire element. Now, in order to balance that, about this point, there must be also a moment existing at this. So, in a planar beam, so at least this one will be there. This is moment about y-axis. Similarly, if it is there here, like this, and in general, because in this beam there is no horizontal force, but had this load been inclined, there would also be an axial force here. Okay, these are all integrated forces. These are all forces acting in the centroid of the cross section. Okay, so there will also be a axial force in general. I am not saying that in general. In this one, supposing there was also an inclined force, then there would have been a force here, reaction at the hinge, and then at the cross section. In order to balance that, there will be. So in general, there will be. So on a planar beam, in general, instead of 6 forces, which we have saw in a general member at any cross section, that was in space. That is the most general case, 6. Now here, if the load is planar, if the body is in the plane xz and loads are applying in the same plane transverse to this, then the beam bends, and at any cross section you will have 3 forces like this, not more than 3 at any cross section. Let us call this as N, this as M, and this one as V, capital V. Now all these 3 forces, V is a vertical force, it is a function of x, M is a moment, this is also a function of x, and N is an axial force, that is also a function of, it could be a function of x in a generally loaded beam. If some portion of the beam is subjected to, I will give you some examples. So in general, this N also will be a function of x. This is called shear force. V is called shear force. So shear force in the beam is V. M is called bending moment at cross section, x is mx. So in the beam there will exist bending moment. So this is not torque, this is called bending moment, which bends the beam. This action bends the beam. This one bends, it does not give you, it does not twist the beam. It bends the beam, so it is called bending moment. Bending moment, and N is called axial force. So at any cross section in a planar beam, you will have 3 forces at any cross section, and they will be varying. They will be functions of x. They need not be constant. It all depends upon the loading case. Now in this case, we will do this. Now I have taken this positive, the ones which I have shown, they are all, I will call at any cross section x, this will be positive. So on a negative x base, what will be the direction of N? N will be equal and opposite like this. What will be the shear force here on a negative x base? It should be downward like this. What should be the direction of moment? It should be like this. So on a positive phase, if once you have fixed, then on a negative phase it will be equal and opposite as per Newton's third law. Okay, so there at any cross section, if you assume on one side something, on the other side there must be equal and opposite forces. So normally we work with a positive phase or negative phase depending upon the convenience of the problem. So now shear force, how do you get this shear force? So if this is the, now I will get the enlarged picture of the depth of the beam. If this is the depth of the beam, this is your x-axis. At any distance, let us say from centroidal axis x at a distance z, because this upward is z direction, this one is z. We are measuring z upwards. So this point I am now taking. What will be the coordinate of this point P? What will be the coordinates of point P, please? This cross section, what is the, so I am taking a point, I am taking a point at a distance z from the x-axis, which is centroidal. X is centroidal axis. So what will the point? It will be xz. Coordinate will be xz. Because width we are taking very small. It is a thin sheet. B is very, very small. Xz. Now at this point here, what are the stresses which are acting? There will be, because this beam is bending, so there must be a normal stress sigma x at any point P on this cross section. At this point there will be a normal stress. See, throughout the depth there will be sigma x acting, and it will not be constant, not like axial force where the whole cross section was subjected to the same sigma x, because that was a P was uniform. P was acting at the centroid and entire cross section was subjected to the same. Is it clear or not? Here, because it is bending, so P will be a function of z. Sigma x will be a function of z. It will be a function of x as well as z, sigma x. What is the other stress that will be acting at any this point here? What is this? I have drawn at point P, one vertical arrow. Shear stress. What will be the designation of this shear stress? Tau x xz. Tau xz. There will also be tau xz acting. Shear stress, vertical shear stress at any point here. So when you see this is the section. Supposing now you are seeing the width of the beam. Let me explain it from any. So I have taken a small element of this one z and this one is dz. This size, this thickness is dz. At a distance z, I have taken a small strip of dz. So now I am seeing this is B and this one is H. This is the cross section. Are we denoting by H or D? What is the depth of the beam? Normally we have been denoting H. H is okay. BH. So this is, so shear stress will be, I think, normal stress is like this, the pen perpendicular to this. Shear stress is within this, like this. So this is the tau xz, which we are seeing it here. Is it okay? So now, is there any doubt? So on the entire cross section, you will be having, at any cross section, you will be having an axial force, a shear force, and a bending moment. Now I am showing on the cross section, I am taking a point and trying to show you, yes, what will be the actual state of stress there. Because stress will be not same throughout the depth. Here it will be varying. So there will be two stresses. sigma x and tau xz, shear stress and normal stress. It's clear or not? Anybody? Okay. So now I will try to tell you. Now if I take sigma x stress at this level at a distance z, sigma x will be same across the entire width. Width is very small. I have told you that this line, this horizontal line will remain horizontal because we are applying load in the plane of symmetry. Or there is another way of explaining. You are applying this load throughout the width. Same load. Then also it is possible. Same load variation, there is no variation of the load, but same load throughout the width of the. So it will remain horizontal. So sigma x multiplied by b into dz. What is b into dz? Is the area, this area, b into dz. This is b and this dz, small dz. Is it okay? Area, small area. So sigma x multiplied by will give you what? It will give you a small normal force. It will give you a small force dF, which will be normal to the cross section. What about tau xz into b into dz? Stress multiplied by area. That will give you again a small force, but it will be a small vertical, shear force. In the cross section only, in the plane of the cross, that means the same plane here, in the same plane this cross section is there, this multiplied by this will be a small force, so that I will call it, because there is already V here total, so I will call it dV, small dV, because small d. So these two forces are. Now I will take this dF. If I take dF and integrate that dF from minus h by 2 to plus h by 2, what is the meaning of this? So dF, if you take dF is a normal force, small normal force. If I integrate from bottom to top, whole area will be covered. That will give me what? So what is that? I have already shown on the cross section. What will be this equal to? N. This will be equal to N. Very good. So N, the axial force is given by. So axial force will be given by, and dF is equal to B into sigma x into dz minus h by 2 to plus h by 2. B can be taken unity also. B is width, small width, sigma x into this one. So this is the total axial force. So this is axial force. AF. A short form acronym of axial force is AF. Axial force AF. What about this V? And dV, integral dV from minus h by 2 to plus h by 2 dV. It will give me what? It must give me capital. The shear force. Shear force on the cross section is dV, small, and that is equal to minus h by 2 to plus h by 2, and dV is equal to again B into tau xz into dz, and this we can call shear force. In short, we call it SF, shear force. Is it okay? Is there anybody having any doubt? This integral, how we are integrating? It is simple integral. A small force we are integrating over the entire area of the cross section of the beam. That is all we are doing. Nothing else. Then the third one I will like to integrate is this. I will say df, because df I have already integrated. But there is one more action, df multiplied by z. Just see. What is this quantity? Huh? df multiplied by z. See here. Sigma x multiplied by area is a small df at a distance z. That multiplied by z will give me what? A small moment. A small moment m. dm. Is it okay? dm. It will give me dm. Is it clear or not? So moment comes from, the moment at the cross section comes from sigma x multiplied by the small area into the lever arm. Lever arm is z. Z means z is distance from the centroidal axis to the point. So m. So m, this one will be defined as m. So this quantity is dm. Multiplied this by, I can write the small dm here. That is sigma x multiplied by b dz multiplied by z equal to dm. So that one comes out to be h by 2 to plus h by 2. B, how much is this df? df is here. df is sigma x b dz into z. So that one is b sigma x z dz minus h by 2 to plus h by 2. Sigma x z dz is multiplied by which is your m. So understand that these moments, shear forces and axial forces are coming out of integral of the stress quantities which are acting at each and every point in the cross section of the beam. They are not quantities in themselves. They are not, they are coming out of the stresses. So I have defined n, v and n the way, I have taken like this, positive. Because my positive stress is always, what is the positive stress on a plane? On a positive stress, sigma x is positive on this plane. Tau x is positive like this. So my shear force, bending moment and axial force, they are derived from the positive stresses acting on the plane. X equal to what? A positive x plane. It is x plane, na? No, you are silent. Which plane is x? This plane is x or not? This is positive x plane or not? Positive x plane. Yes. So I am defining these. So right in the beginning I told you that I am going to take now. This is slightly different notation from whatever is given in your book. Okay. Book shear force is on a positive is vertical, but moment is moment is the just the reverse of this. So moment is this way, positive he has taken. Popo. Because at that particular point they have not related positive stresses to the moments and shear force. But we are relating here because our moments, shear force, they are coming from the positive stresses. We don't want to confuse again. Otherwise I would define it by negative sign. So I don't want to define it by negative sign. Is it okay? Huh? So this is will be my positive convention. Okay. So at any cross section, you have three quantities in a plane beam. This is a very important concept, and unless you shear force bending moment diagram you understand thoroughly, you cannot understand. In fact, this I consider more fundamental than torsion of circular cross section. Torsion, one can take it little later because torsion comes only in specialized members, which are shafts, in machinery, etc. But bending is very very common. All buildings you have bending of beams. Yes. Huh? What about V? V is upwards. So V is V plus P minus P by 2. So how much? So V will be equal to minus P plus P by 2. So that is minus P by 2. It is constant. But the sign has changed. The moment my point is gone beyond P, loaded point, the sign of shear force has changed. So sign will change along the length. So then M is how much? M is at this point. Please tell me quickly. P by 2 into this M, P by 2 into X minus P into X minus L by 2. Is it okay? That is how much? Px by 2 minus Px plus Pl by 2. So how much is this? How much is this, please? Quickly. So Px by 2 minus plus Pl by 2. So that becomes equal to how much? P by 2 L minus X. L minus X. So at X equal to L by 2, it will become how much? PL by 4. So if I want to, from here, this is L by 2, this is L. The beam. So how much at L by 2? L by 2, PL by 4, positive, the same value. And then at X equal to L, it is 0. So it comes down. What about shear force? So this is bending moment. What about shear force? Shear force is, it is saying that shear force is negative. So from here, L by 2 to L, shear force comes down and this is negative. So this is shear force. Okay. Now on the total, if I want to draw the total length, shear force. So shear force diagram will be looking like this. First positive, then there is a change, it comes down, then it is becoming like this. So this is positive, this is negative. This is P by 2, this is P by 2. Bending moment, it is going like this and this is positive. Okay. Is this okay? So this is shear force diagram, total beam. Shear force diagram, SFD. In short form, it will be called now SFD. This is SFD. This is what? What will be this then? BMD, bending moment diagram. Bending moment diagram for the entire beam is like this. So this is one important. Okay, as far as this one is, so bending moment diagram, axial force diagram and shear force diagram as they vary along the length of a beam is an important thing that one should know. This is the basic of solid mechanics and you must know very, very carefully. Thank you.